All right, so last time we talked about, let's see, I've got sets over here. We also talked about, let me scroll back up. So here we go. Last time we talked about propositions and about sets. We're going to focus more on propositions today. And so just to remind you, a proposition or a statement is a sentence that is either true or false. It has a truth value. If it's ambiguous or undefined, not a proposition. And we'll see this a lot today. And so if we know what P is and what Q is, then we can just refer to them by the variables P and Q. We also talked about sets. We'll catch up with that on Friday. Okay, scroll down. Question? Okay. All right, so once we have the idea of what propositions are, there's a few axioms that we need to know in order to go forward. One is negation, which is let's say if we have, it is cloudy. If that's our proposition and we call it with a variable P, we can denote this kind of right angle looking thing. And this is not P or negated P. And so this symbol is, what did I have that in LaTeX? Switch to editor. That is \neg in LaTeX to get this symbol. And so this just means that we take the truth value and we flip it to the opposite. So if it is cloudy is true, there's clouds in the sky right now, then when we negate that, that means it is not cloudy. And so maybe like it's sunny or trying to think of another option. I think cloudy or sunny or raining, but isn't it cloudy when it's raining? So the idea is when we put this symbol in front of P, then we negate the sentence. So the truth value flips. And it turns to the opposite. So we're going to write truth tables. If you're in 310, you'll probably already know how to do this. You'll be doing it a lot. So we're going to write a truth table, which is basically if I have some variable P, I'm going to look at what are all the possible values for P and explore what that means for the different equations that I'm trying to write, the different logical equations. So if P is, well, P's got only two options, right? True or false. And so let's look at not P. If P is true, then not P is false. If P is false, then not P is true. Right? We just flip it. Next thing to talk about is conjunction, which is also called and. And so if you've done programming, then you know how this works, where we denote it. So we need two variables here. We'll call them P and Q. And the conjunction we denote with this little hat thing. In LaTeX, we call it \wedge. And this is read P and Q. And so this is true if both P and Q are true, and it's false otherwise. Question.
For the like wedge, are there any other ways of doing it? Because I am in 310 right now. We've been using like dot or multiplication. Like I just put the numbers side by side.
Yeah, I think your notation kind of depends where you are. I think so the book uses the wedge because that's like the more mathy way of saying it. I think the dot also works as long as you're clear on what the notation means. Yeah. So the thing about notation is there are some standard things, and so like the using the wedge is standard in math. Um, in other situations, it could be different notation. What really matters is consistency. And so we're going to talk about or next, and so it's important that you don't say that, oh, this is or, right? That's just going to confuse everybody. So difference in notation is fine, just stay consistent. All right, so let's do a truth table for P and Q. So one option is for both of them to be true. P is true, Q is false. The other pair of them are false. Like we swap that, and then the final option is that they're both false. And so by our definition, this is our axiom, that if they're both true, then this is true. Otherwise, it has to be false. And similarly, we can say what is this called? Disjunction, which is the logical or, is written P and this symbol, which is V, we read that P or Q. And this is going to be true if either P or Q is true. And then it's going to be false if neither are true. So that's our definition. Let's put it into the truth table. Here, let me move this down a little bit. That way we can see all that at the same time. And so let's see P or Q. And so it's true if either of them are true. So the first one is true. The second one, P is true. So P or Q is true. The third one, Q is true. So this is also true. Then neither of them are true. So it's false. And again, this is logical or, so this shouldn't be new. Okay, so these are our axioms. So we define what P and Q is. We define what P or Q is, and then we define what negation means. So not P, just copying it from above, that's false, false, true, true. And then not Q is we just flip the values of Q, false, true, false, true. And so once we have this, we can build more complex systems where if we have this notion of and, or, and not, we can combine them to make pretty complex statements. So let's do, we're going to do example 14 from the textbook. I'll put it on the right page, page 39. And so the example I'm going to have you do is talk with your neighbor, and we've got P, Q, R, and S. All four of those are statements. They have a truth value of either true and false. And so I want you to write the statement in words, each of these Q, like Q or R, Q, and S. Write it in words and then decide its truth value. Go for it. So an implication or a conditional is something that we write in the form of P, this arrow Q, which we read P implies Q, or we say if Q, then P. Nope, that's wrong. Left to right, we read if P, then Q. We can say P is sufficient for Q. And then, so these are all ways of writing it with P coming first. We can write it with Q coming first, where we could say Q if P. So we still have, so there's this notion of like if, then. So if on the left-hand side, then on the right-hand side. And so that's how we say Q if P, or Q is necessary for P. This one always confuses me, but if you think about it, so if we have some statement P that has been satisfied, and this statement is true, if P then Q, then when you have Q, you're gonna have P. So if, like, let's say, if I'm on campus, then my car is here. If my car is here, then I'm on campus. So if you only see Q, then you can infer that, oh, I'm on campus. So if you see my car, then I'm on campus. So my car being here is necessary for me to be on campus. Because otherwise, how am I going to get here? Okay, so we've got the some practice here. Let's say P is you aced your final exam, and Q is you aced Math 240. So the example in the textbook is, let's say you go to the professor and you're like, what do I need to do to pass the class? And the professor says, ace your final exam. And so here the logical statements are you ace your final exam. That's going to be true or false. Either you get an A or you don't. And Q is you pass Math 240, which is either you get a C or better, or you don't. So those are our two options. And so let's talk about each of the cases. So we'll build our truth table as we go. So the possibilities are all of those, right? Those are the only possibilities that these two variables can all have together. So let's look at P implies Q. So if you ace your final exam, then you pass the class. If you ace your final exam, and you pass the class. So we're going to be evaluating the veracity. So if you come to me and say, what do I need to do to pass the class? And I say, ace your final exam. So you're going to be evaluating the veracity of my statements. So was what I said true? So if you go and ace your final exam and you pass the class, was what I said true? Yeah. You aced your final exam, you passed the class. If you aced your final exam but didn't pass the class, was what I said true? No. So you didn't pass even though you aced it. And so then I would have been lying. If you didn't pass the class, or if you didn't pass the final, if you didn't ace the final, but you passed the class, was what I said true? This is where it gets tricky. So like the situation here is, in this case, you may not have needed to ace the final to pass the class, but you still passed the class. So in this case, this is true. And this is, let's see. Yeah. So this is vacuously true, meaning that even if I have, even if you passed the class, in this case, you didn't need to ace the final to pass the class. So that's the tricky one. But if you don't ace the final and you don't pass the class, is what I said still true? Right. So this one is true where you didn't ace the final, didn't pass the class. So that one's the tricky one. Let's look at the other way around. So if you pass the class, then you ace the final. That's what we're looking at. So if you pass the class, does that imply that you aced the final? Sure. If you passed the class, or if you did not pass the class, but you aced your final, this is also the tricky one. If you passed the class but didn't ace the final, this is false. And then if you didn't pass, nor did you ace, then that is true. So this is me saying if you pass the class, then you aced your final. And so this one is kind of vacuously true. Yeah. So that's where this analogy kind of breaks down. But these are the definitions. These are also the definitions for this notion of P implies Q and Q implies P. So we can kind of think through examples to it, but again, these are going to be some of our axioms where TFTT, TTFT. And so yeah, so these are our axioms. I'll try and think of a better example. In any case, we need to talk about something called a biconditional, which is if we have P implies Q and we have Q implies P, then we can have the case where if both of those are true, where we say both P implies Q and Q implies P. If both of those are true, then we can write it as P and then this double-ended arrow with Q. This is a biconditional. And so the way we say this is P if and only if Q. And this is our code word for this double-ended arrow. And it's abbreviated PIFFQ. We have P is necessary and sufficient for Q. So remember, we have the necessary and sufficient conditions for just P implies Q. Now we say P is necessary and sufficient for Q. And then the one the book says that this, I don't like the way this is, but it also just makes sense. So if P, then Q, and conversely. I think I missed a. Okay. I missed a few words. These are also in the textbook. So if we have P implies Q, the whole thing is an implication or a conditional. P is a hypothesis. Q is a conclusion or the consequence. And P is also called the antecedent. So those are our terms for you. All right, now let's do activities. So I've got this up on Canvas. Let me see, can I fit them all on one page? I cannot. So I think for the rest of the class, we'll work on these. If we end early, I have additional like homework problems that you can start to work on. So yeah, work with your neighbors, talk it through, go for it.